Hello, I'm Richard Tyrone Jones. I'm a poet and a Cambridge graduate Ponce, and therefore a naturally very curious person. So when, aged 30, I found myself diagnosed with heart failure, a big heart, I decided not only to write a one-person show about it, Richard Tyrone Jones's Big Heart, but also, supported by the Wellcome Trust, to go out and interview some experts on heart failure to try and find out more. My heart almost died of dilated cardiomyopathy, and all I got was this lousy t-shirt cut up by the crash team. Today I'm visiting the London Chest Hospital, but I'm not here for an appointment. I'm here to visit Professor Anthony Mathur, who is one of the world's leading experts in cardiac stem cell research. Now, stem cells are cells which are dotted around the body. They're not muscle cells, they're not nerve cells. They're there to carry out repairs to whatever gets damaged around in our organs. Now, when we're an embryo, we're made up completely of stem cells. They're called pluripotent cells, which means that they can develop into anything. And salamanders and zebrafish have many more of these pluripotent stem cells in their bodies throughout their life. So if you chop off a fin or an arm of a salamander, then they will eventually grow back. Now, what Professor Mathur has been doing is taking stem cells from the areas of our bodies that have the most, which is the bone marrow, and bone marrow transplants have been going on for about 30 years, because that's where most of the stem cells are. And he's been taking those stem cells and injecting them into the heart in clinical trials to find out if they will actually improve heart function. Now, he's been doing this with the victims of coronary heart disease, of heart attacks, and of dilated cardiomyopathy, which is what I have. So let's take my big heart and see if Professor Mathur can fix it. So Professor Mathur, how were you drawn into the field of cell regeneration? Was it something that you wanted to do ever since you were a little undifferentiated ball of pluripotent embryonic cells?
In childhood, I was always taken to these programs which looked at either engineering solutions or whatever to dealing with human disease, so the so-called bionic man type thing. And in fact, I tried to pursue some of that at university, but didn't get particularly far, and that was trying to harmonise engineering with solving biological problems such as limb amputation or the like. And it's not till I'd got through medical school and decided to embark on a career in cardiology that the whole regenerative theme came up. So I did my PhD at University College, and that PhD was based around stem cells, but in a slightly different capacity. It was looking to see if stem cells in your bone marrow might actually cause heart attacks by making the cells that normally stop your blood from clotting, called platelets, making them more reactive. And so my research was all around that theme at the time, and of course, unbeknowingly, I was also not just dealing with the disease process, but also a potential solution. So I was handling stem cells. And shortly after I got my PhD and became a consultant, I decided to embark on an academic career in which I'd spend half my time doing research and half my time seeing patients in the clinic. It dawned upon me that actually trying to combine that with my PhD and perhaps my childhood interest in trying to repair damaged limbs and organs, it's not until 2004/2005 that we had our first trials that we put forward. So I guess within a space of 5 years, from the concept of now that stem cells seem to be a way of embarking on this regenerative medicine quest to try and repair the damaged heart, the 5-year time span was what it took from that concept actually turning into clinical trials that we embarked on in 2005. So I have great respect for the engineering solutions, the artificial hearts and the like. But yes, I do believe that ultimately the solution relies in biological solutions, so growing new heart muscle or perhaps even growing new hearts.
How do stem cells know what to turn into?
There are two schools of thought at this moment in time about the whole field of, let's call it cell therapy, not stem cells. And the reason we make the distinction is that stem cells, the terminology stem cell actually refers to a very specific cell type. And that cell type is the type you find in the human embryo, which has the ability to become any cell and to divide into a vast number of cells and create the billions of cells that make up you and me. And bearing in mind you start from 2 cells, you can understand that the potential of those 2 cells is colossal. That's the true stem cell, and if we're able to understand how to use those cells, then yes, repairing parts of damaged hearts, damaged limbs, or the brain, for instance, using those cells becomes a concept of actually growing new heart tissue, new brain tissue, new liver tissue to replace the damaged tissue, and it's totally functional. And I'd say that's the holy grail of regenerative medicine. Along the way though, there's an awful lot that we can learn from our, I'd still say, relatively basic understanding of the field of using cells. And in the case of the research that we're doing, these are adult, we call them stem cells, but strictly speaking they're called progenitor cells. So they don't have the same capacity as the embryonic stem cell, but they have a capacity to actually partake in repairing organs. Yeah. And in the heart, whilst we'd like to think that what we're doing is growing new heart tissue, there are also lots of other mechanisms that these clever cells can actually enable in the heart to improve heart function and ultimately improve how a person feels. And it's probably those functions that these cells have that we're tapping to in the first instance on a long journey that will ultimately lead into us understanding how we can make cells grow into the cell of choice that we want and the numbers that we want. It's unlikely that they're going to grow vast new amounts of heart muscle, but there are other means by which these clever cells can actually restore heart function. So the 3 trials that we're looking at are really designed to cover the spectrum of disease that patients in the UK suffer with if they've got a heart problem. The first is a heart attack, so the first trial is to try and understand whether a patient having a heart attack comes into hospital, comes to our centre where we open up the blocked artery, which is what happens when you try and treat a heart attack, and then inject their own cells back into them soon afterwards, whether that process can actually restore the damage that was done and actually improve on best medical care that we have at the moment. It's the heart muscle that we're trying to prevent from getting damaged by the heart attack. Okay, so the progenitor cells, the cells we're taking from the adult bone marrow, are there in an attempt to reverse the damage that the heart attack is trying to cause, because that damage occurs over several hours and often several days. So putting these cells back in early can prevent some, if not all, of that damage, hopefully restore heart function to the way it was before the heart attack, and in a way sort of turn the clock back as if they'd never had the heart attack. So it'd be nice if they didn't have to take all the tablets and have all the consequences that a heart attack normally leads to. Then the next trial we're doing is to take the group of patients who've had a heart attack some time ago that's caused significant damage to the heart despite best medical care, who are limited by their symptoms because their heart isn't working as an efficient pump. They get breathless, they end up in hospital quite a lot, needing infusions to try and get rid of the fluid that collects when the pump doesn't work efficiently. And trying to address the question whether we can use their own cells, injecting them back into their hearts to try and recover some of their heart function that they had before they had their big heart attacks. But on average, these patients had their heart attacks about 3 years ago, so they're well established along a heart failure pathway. And the final group of people that we're looking to see if their own cells have a potential benefit are those with a condition called dilated cardiomyopathy, who in essence haven't had a heart attack that involves a blockage of an artery causing destruction of the heart tissue, but have a condition in which the heart muscle doesn't work properly for a number of reasons, and by that process starts to weaken the pumping action of the heart, causing similar symptoms to heart failure. And again, the question there is, will a patient's own cells prevent potential progressive process or even reverse the process to restore their quality of life?
And about how many patients are involved in the trials?
Our overall program has involved over 200 patients. roughly evenly split between those 3 trials. The hardest group to try and get involved in this research are those patients coming in who are having heart attacks, because of course a few minutes ago they were perfectly well doing something. Their own illnesses, their own future, their own vulnerabilities hadn't been something that, with respect to their health, hadn't been something that they'd been addressing. That might be the best time to give cells. But of course, trying to explain that to somebody who's just coming to terms with the fact they've been scooped up in an ambulance and brought to hospital because they've got something very importantly, going wrong with them, is very difficult. And you could also argue that trying to get consent within this very acute environment where somebody's just been brought in very unwell is a misnomer in itself. And how can you explain all the facts that you need to in such a short space of time to somebody who's got so many other things on their mind?
And would you also need a control group for that kind of experiment? So you'd be saying to someone, well, we're going to inject these cells into you, but there's a 50% chance that actually we won't be doing this, and so it might not help you at all.
Absolutely, and trying to explain that. So we do have that control group, and trying to explain that in a short space of time, all the rest of it is very difficult. Whereas your more chronic patient gets a chance to think about it. We can spend some time explaining why the trial is done in that way, which is the gold standard way of doing trials, to use a control group, and hence it's a much easier group of people to recruit from. It's a very small number of cells compared to the number that you need to repair the damage of a heart attack, but that regrowth of cells suggests that there are stem cells in the heart. And what it's thought is that these stem cells live in clumps in particular places. So in the heart that you're holding, there's some that believe that the stem cells actually reside in a lining that goes all the way around the heart, the so-called epicardium, and you find them more or less evenly spaced all around the heart. There's some that have demonstrated or believe that stem cells live in so-called niches, and the niches can occur in the main pumping chambers of the heart, which are down here.
I can open my heart.
Yeah, but residing in the heart muscle itself, but also in the atria, which are the chambers at the top, again in the heart muscle wall.
This one's a little bit more difficult because it's second-hand,
but what's clear is that even though there's evidence that these cells exist, they aren't up to replacing the damage that occurs in a heart attack or the overwhelming damage that occurs in dilated cardiomyopathy. When it comes to using true stem cells, the cells that occur in the embryo that have the potential to keep growing, we don't have all the answers as how to stop them continuing to grow. And that's why if you are to use these cells now, true stem cells, embryonic stem cells, one of the risks is that they form cancers, which are cells that have lost their ability to control the amount that they divide. The adult bone marrow cell doesn't carry all those problems with it at this moment in time, to our knowledge, given that around the world several thousands of people have now received adult bone marrow cells to try and treat their heart condition, and we haven't picked up some of the problems that you would predict from using embryonic stem cells, for instance.
So when will you be ready to publish your findings, or can you give us any spoilers as to the results? This
is a long-term condition, and although you might get a nice publication by looking at what happens to your patients 3 months after they've had their cells, really you're more interested what happens to them a year, 2 years, 5 years down the road. 5 years is going to be a bit too long to wait for the first publication, but we designed our trials to look at what happens to them a year after they've had their cells injected. And so we've just got to that point in one of our trials. We're actually looking at the results, and they all look actually very, very promising. So we're in the process of publishing those results.
So where has the funding for all of these trials come from?
So we've put the money together for a number of sources, but the backbone really has been the Heart Cells Foundation, because they're still raising money to further this research. What's nice about what we're doing with cell therapy is that everyone, that's patients and doctors alike, are sharing the experience. If this were a drug, it would still have a code name, it would be in a black box concealed somewhere in industry, and they'd be running their studies, not making anything of it, it wouldn't be in the media, nobody would know about it, and maybe in 5 or 6 years' time they'd release the drug for commercial use, for sale essentially, and then you'd hear the big splash and all the papers and things would come out. This journey about cell therapy driven by academia has been a partnership between patients and doctors from the very beginning, in which we've shared the journey. And so one of the problems is everyone's had this expectation that we'd have all these results really quickly. I can say in the grand scheme of things, the development of a new drug or device, these results are quick. It's just that nobody appreciates that there are often 20 years behind the development of a drug before we actually see it and it hits the press. So we just have to be patient, but we're doing well.
Do you think that's the timescale before regenerative cell therapies will be used and rolled out throughout the NHS, about 20 years?
No, I'd say it's less than that, because the pragmatic approach of going to collect the data by forming bigger trials is actually moving forward in a field which, as I say, does not have much in the way of industry support for what academia is doing. And therein lies the problem, that to do the big trials costs millions of pounds, and we have to somehow raise the money to do that. But that's all part of the regulatory pathway you need to deliver this as a treatment. So I think 20 years is too far off. 5 to 10 years, yeah, maybe.
Could stem cell therapy make a patient stronger than they were before?
In theory, yes. I mean, what we're hoping is that it's going to strengthen the heart, and I guess what you're referring to, or could be referring to, is athletic potential. So if you can use stem cells to improve muscle bulk, for instance, then in theory you could produce somebody that's stronger. But of course, athleticism isn't just all about strength, it's about coordination and all sorts of other things, and whether stem cells will have that ability too, you know, who knows. So in theory, yes.
Well, you don't actually have any stem cells that we could have a look at?
Not here.
Microscope?
No, I'm afraid not.
Where are they kept?
Well, we take the cells from our patients here, but they go over to our stem cell processing lab, which is over at the Royal London, and then they're brought back here for the actual infusion process.
It's not that I want to steal them and inject myself with the stem cells to give myself superpowers at all. Just to put your mind at ease there, Professor Mathur, that's not...
No, thank you for that.
Not
yeah.
what I'm planning at all.